Good afternoon. Today we are going to look at multiple recursion. We already saw binary recursion and linear recursion. This is multiple recursion. So what is multiple recursion? In binary recursion, there are two recursive steps. In multiple recursion, it can be more than two, for example. So the recursive steps can be 3, 4, or it can even be, it can also depend on the input size. So that's multiple recursion. And what is the problem we are going to solve today? The problem we are going to solve is what is called as mini Sudoku. And you might already know Sudoku. It's basically filling up a 9x9 grid with numbers from 1 to 9, but it has to satisfy some properties. And in this example, we are going to see what is called as mini Sudoku. And in mini Sudoku, it's a 4x4 grid. Okay, you can see the screen. It's 4x4, so each cell can have numbers from 1 to 4. As you could see, any cell can have numbers from 1 to 4. And the next property which it needs to satisfy is that every row, a row can contain exactly a number exactly once. That is, no number can be repeated in a row. Okay, the number 1 can't appear 2 times, number 2 can't appear 2 times, etc. And also remember that every cell should contain 1, 2, 3, 4. So the first row is a permutation of the numbers from 1 to 4. That's rule number 1. Rule number 2, that's rule number 2. Rule number 1 was every cell should contain numbers from 1 to 4. Rule number 3. Rule number 3 is that no number is repeated in any column. It's the same as rows. Every column is basically a permutation of numbers from 1 to 4. Next is rule number 4 is every group of 2x2 cell, right? So this is basically a 2x2 group. Every 2x2 group also contains a permutation of numbers from 1 to 4. That is, no number is repeated in any 2x2 group. Here, 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 here. In none of these 4 groups, a number is repeated twice or more. Okay. So this is mini Sudoku. And how do you solve this mini Sudoku? So what is the question? I give us the problem instance like this. I give you a partially filled Sudoku. So here now, as you could see, the numbers 4, 2, 3 and 4 are marked in the Sudoku board. You're supposed to fill the rest of the cells. Like that is, replace the zeros in the rest of the cells by numbers from 1 to 3, 4. Such that all these 4 conditions are satisfied. Okay, that's the objective of mini Sudoku. Now, so we are going to solve this thing recursively. That's our aim. So before we start, let me write a function to print the board, because we'll use it later also. In the end, if we solve it, we'll print that board. We'll use that function to print it. Now, so I'm going to write the function. So print board. Okay. And what does it take as input? It's going to take the board as input. So I just took it as input, and what do? I'm going to go, 2 integers I and j are going to basically go through each cell row column wise. Okay, each cell of the board. That's the idea. Okay, now what do? Print %d with a space, comma, board ij, and after every row I'm going to print a slash n. That is, it's going to come to the next row. So let me see whether this board is printed correctly by my function. If it is, we can move ahead. Otherwise, we fix that function first. So this is one way to approach writing a program. Don't just write the entire program at one stretch and solve it, and then you compile, it doesn't run, all sorts of problems will come up. So the best thing is do step by step, write a function, check it's working correctly. So that's what we just now did. I just wrote a function, I'm going to check it is correct. Okay. Okay, so this is GCC. I'm going to compile this GCC Sudoku.cc, lot of errors. What is the error? Okay. The variables I and j are not, I mean the compiler does not know what is I and what is j, right? Because we didn't define. Clear. It's clear. Now I can print the board ./a.out. The board is printed exactly as we wanted, 040, exactly. Good. Now we want to solve it recursively. So what is a function? I'm going to write a function basically here, int solve Sudoku, and it's going to take the board again. Just took the board. And what is the idea? What is the idea here? To use it recursively, the idea is the following. I'm going to fill, just let's say I take this cell. So I'm going to go through all the cells, look for cells which have 0 in it, and I'm going to fill it with some number from 1 to 4, and then recursively solve the problem with this extra filled in value. That's the main idea. Okay, that's the main idea for the recursive step. And what is the base case? The base case is basically going to be every cell is filled in, and in that case we just say so actually there are two base cases. One base case is every cell is filled in, and we just print out the board. And the other base case is that it's not possible to move ahead. You can't fill in a letter without violating, fill in a number without violating at least one of these conditions given below. In that case, what we do is we just return saying it's not solvable. So there are these two base cases which is going to happen. So you should notice here that the base cases are kind of tricky here. It's kind of hidden in a much more it's not as revealing as the previous examples we saw. Okay, right. So let's just first write the recursive step, and we will fill in the base case as we go ahead. Okay, so what is a recursive step? I'm going to go through each of the cell, and I'm going to check whether that cell already contains 0. If it does not contain 0, I mean if it's already filled with some number from 1 to 4, nothing else to be done, right? On the other hand, if it contains a 0 value, I'm going to fill it with some value other than 0 and call this function recursively. That's the idea. Okay, so first I check whether the cell contains a non-zero number. If it contains a non-zero number, I don't have to go ahead. So this is the shortcut, continue. What does continue do? It just basically takes you back to the beginning of the for loop. The for loop is executed once. You don't see, I mean, it does not come here. The condition above is true. Okay, that's what happens if you use continue. Now, okay, so I have just now checked that the board is basically 0. If it comes here, it means that is board ij is 0, right? Okay, so the board ij is 0 there, and now if it's 0, I want to fill it with some number. Which number? Let's go through all the numbers. So numbers from 1 to 5. Okay, so I can have size +1 and k++. Okay, I'm going to try whether it's possible to fill in with that number. And how do I do that? So we'll worry about that logic. Okay, so what is it we need to do? We need to basically check if I fill in with that the ij position with the number k, will it violate one of these conditions? That's what we need to check. So that logic I'm going to do it later. First, let me just let's just write a function, assuming that there is a function to check for that logic. So valid, if valid whatever valid board. So it does not violate any of these conditions. Okay, okay, or if not violating. So if it's not violating the with I comma j comma k, right? So if the not violating function basically returns 1 if that it's safe to put the kth value in the ijth location, right? And so if it's not violating, what does it we need to do? If it's not violating, it's good. I just fill it, right? I just fill the ijth location with k, and then I'm going to recursively solve it. So I just call it recursively. I just call that function recursively. Now what is it we need to do? Okay. We need to check whether this, what does this function return? This function return. So let's just write what this function does and what it returns. The function solves the Sudoku problem if possible. It also prints the solution in this case, and as input takes the board position, and as output returns 1 if success, otherwise returns 0. So success means if solution possible. This is what that function does. Okay, so now if solve Sudoku returns 1, what does it mean? It means it succeeds. So if it succeeds, then you don't have to continue doing anything. We just return 1 because it's already a success. I'm not going to continue doing this. We just go ahead. So comes the next thing. Next thing is it's not a so it comes down if it's not a success, right? If it's not a success, what is wrong? It means that this assignment, ijth assignment to k was wrong. So I replace it with 0 and then I go to the next value of k assignment. Okay, that's what we do. All right, is it clear? Okay. So this much is clear, right? So I mean, this is recursively solved. Now only thing is now we already solved the base case. Now finally, no, we haven't solved the base case. Okay. As we said, 2 base case. So this is the recursive step. So how many recursive steps are there? As you could see, size into k many recursive steps can happen at any point of time, because if you write this entire for loop in like we open up the for loop and write it explicitly, it's going to be size into k many recursive steps, right? Now what about the base case? The base case, we said it's kind of coming to the lowest position where all positions in the board is filled. Okay, in that case I'm going to say good, things are I mean everything is filled means we are right, and then it's going to return success and going to print the board. Okay, so I'm going to, so how do I check for that? I'm going to have a variable full, which is right now 0 because it's not full. Full means everything is filled. Right now, when does full become okay, so right now I'm going to assume full is 1, and if it comes here, what does it mean? Okay, so if it comes below this, it means that board of ij is equal to 0, right? That means it was not full. So I put 0 there to make it not full. Okay, that's basically a boolean variable which is going to store the fact that it's not full. Right, now I come here at the end of the for loop and I just check whether it's full. If it's full, means it never came here. That means everywhere it's not equal to 0. In every ij position it's not equal to 0. In that case, I can just print board with the board position, and I'm going to return 1. Is it clear? Okay. and otherwise I have to return. Yeah. So let's see why did I return 0. We'll see. Okay, this is one case where if the board is full, I have returned 0. Now when do I reach here? So the board is not full, and if it was something was a success, then I would have returned 1, right? At least in one of the k values I would have, it succeeded, I would have returned 1. Now it reached here because it neither succeeded nor full, and that's why it's returning 0. Okay, so let's now declare all the I, j, k and success, define all these variables, and that's it. Let me just have, okay, is it clear? Right, now we are left with just doing one thing. What about this function not violating? So not violating, we have to basically look whether all these conditions are satisfied. So I will keep it here so that we can look what we are interested in, right? Let's keep it there, and I'm going to write the function it's not violating, and it's going to take the board, and it's going to take the ijth location, and it's going to take the value k to be inserted there. Okay. Now first thing to check is it's the row and column, the value k is not already present in the row or column. Okay. So how do I do? I just have some variable t going from 0 to t is less than size and t plus plus, and it just checks for if board I t is equal to k, then it just return 0 because it's already has a k value, and then it's not possible, right? On the other, so similarly I just have to see, so I'm basically looking for both column and row, and I have another okay. So now so first we check that I fixed the row I, and I checked the entire row. There is no k repeated. If some k is repeated, I return 0 saying it's violated. Similarly, I looked at the column. I fixed the column, and I look at all the entries in the column and see whether the k is incorrect. Yeah, which row and column did I fix? The row is I and column is j. Okay. Now comes the next thing. So that's basically takes care of my rule number 2 and 3, and finally we have to take care of rule number 4, which is about the 2x2 box. Okay, now we're going to do some like a slight smart trick. Okay, so my I and j is going to come somewhere. Let's say it's going to point in one of these cells, right? Let's say here or here or here or here. Now in that case my ij is going to point to one of these 4, and then I want to go through all these 4. So what I do is the following. I'm going to play a neat cute trick to get basically this point. Similarly, if ij is going to be one of this is in one of this group, I'm going to play this. The same trick will give me this point. Okay. Similarly, in this group it's going to give me this point. Similarly, in this group it's going to give me this point. Okay, that's the neat trick I'm going to do, and it's very easy to do. And what I do is the following. And okay. So what I did is, so what is I divided by 2? If I is 1, let's say I is 1, right? So I is 1 means this here. I0 means this row, I1 means this row. Right. I divided by 2. 1 divided by 2 is 0 because it's integer. So 1 divided by 2 becomes 0, and it comes here into 2 is 0. So it's basically going to be here. So ith row so if we give first row becomes the 0th row. Similarly, the first columns becomes the 0th column. So anything in here will go here. Okay. And now let's look at here. 0, 1, 2, 3. The third row. Third row. 3 by 2 is 1. I come here. Into 2 is 2. So I come here. Right? So I am in this row. Okay. So if you give me this row, my T becomes this row. Similarly, if you give me this column, my L becomes this column. So basically anything here will take me here. So if that's the case, once I am there, I just check basically all combinations. So I could have written a for loop for this, but this is good enough. So I just check whether all these positions are does not have the k value. Okay. So if none of these positions have the k value, I just return 1. Okay, I will have to basically have integer t and l here, and that's it. This should work. Did I print the board somewhere? Yeah, I have printed the board here. Now, okay, let's compile and see. If it doesn't work, we will see. Okay. We never call this function, right? So I just printed the board. I'm going to print so if it comes here, I'm going to print success. If it comes there, I'm going to success. Otherwise, yeah, otherwise nothing happens. Okay, nothing is better. We can just so it's success. We have, as you could see, the original in the original problem it has 4 here, 2 here, 3 here, and 4 here. It's exactly what has happened here, and we have succeeded. It's returned correctly. The Sudoku is solved. It's good. Yeah. Right. So where is the base case? This is the base case, right? I'll just note down that this is the base case. Right. So as you could see, this is kind of little, and okay, return 0 is also base case. We did not succeed in filling. Okay. Multiple observations are required. One, it's multiple recursion here happening, right? The recursive step is called many times. How many times is it called? Size into k. In the worst case, sometimes maybe not. If the continue gets called, it does not come to the recursive step, but it's called multiple times. Second case, it's very difficult to see the base case. It's hidden inside all these intricacies. And thirdly, we had to check this fact, right? So we have to check this fact that the input parameters or the board has to decrease. Has it decreased at every step? Otherwise it will keep on going. That's something we need to check. Has the input value decreased? Yes. What has decreased here? What has decreased is that the number of zeros in the board position has decreased. At every instance of this function call, the number of zeros has decreased. Initially there were only 4 non-zero values, and the next time the Sudoku board is called, the recursive step is called, at least one board ij is set to k, where it was 0 earlier, such that position is set to k and non-zero value, so that is the board, the number of 0 positions in the board is decreasing at every recursive step. As we said, it's tricky, right? Okay, so this is what, this is one takeaway, that in reality all the 3 steps are not as straightforward as a Fibonacci sequence or the other examples we saw, and things can get a little tricky, but you should think you should always think, what is the base case? Have I covered the base case? What are the base cases? Have I covered the base cases? What is the recursive step? And is the input parameter decreasing? Only if I can ensure that the input parameter is decreasing, can I ensure that the program will stop. Okay, so try this thing out, how it works. And one thing you can try as an exercise is something you can try to do, is that you can calculate how many times this solve Sudoku function is called, right? Keep a counter value on how many times the solve Sudoku value is called, and check this fact. Okay, how do I do that? You can have a global counter, for example here, int count, which is, you can set to 0 in the beginning, and every time you call here, you're going to increment it, right? And once you come, I can just do it here. The count is 89. Okay, and you need to think why this 89 many times this recursive function got called. Okay, recursively 89 times it got called. This is something you need to think, and this is there is a reason why I chose mini Sudoku and not original Sudoku. When you try at home, you can just try it. You can try extending the size to bigger numbers and see why it may not work. Let me just reveal that if you go for this main Sudoku of 9x9 board, your program will never stop. It's going to run forever, in the sense that even if the life of it's going to run even after the earth dies. So the number of steps involved is more than the life of the earth. The number of the time it will take is more than the life of the earth. That's one important takeaway. You can try that out. Okay, not that, but you can just start running it and then stop it after some time and look at the count, etc. Okay, then thank you.